book. This is a demonstration of how to use my Neato physics notepad. Alright, so here's a physics problem. We have a brick sliding down a slope. We want to know how fast it's going when it gets to the bottom. So the way we're going to solve this is using conservation of energy. So the kinetic energy at the bottom is going to equal what the potential energy at the top was. So let's pull up those two equations. So looking for kinetic energy, looking for gravitational potential energy. Great. So these are two different equations that we have. Now I'm going to declare that these two are equal. Those are referring to the same thing in both equations. And we'll set the masses equal as well. So now let's solve for velocity. And we get this equation. And this is in fact the result of solving for velocity in this equation here. But we'd like it to be in terms of these things rather than these things. So I'm going to drag out of the kinetic energy into this potential energy equation. What that means is sub in for kinetic energy the equation for kinetic energy you get by solving this equation I'm dragging into. And if I do this, then I get root 2gh, which is in fact the algebraic solution to the problem. So let's sub in those numbers we had. So we had 2.3 kilograms for the brick, and drag from mass to that to set that, and its distance was 4.2 meters. Now, of course, it's totally dumb of me to have given that answer for the mass because it doesn't actually matter. But whatever, too late. 9.8 meters per second. Set gravity to that, and here we go. So we have the answer to the question. So let's do another one. So we have a current of 5 amps and a 10 ohm resistor for 4 minutes. We want to know how many coulombs and how many electrons pass through any cross-section of the resistor in this time. Let's look up amperage. We have current. So we see that this equation makes it look like to get the number of coulombs, we're going to be able to do it without caring about the resistance of the resistor. We just need to know the amperage and the time, which we already do. In particular, we had 5 amps, and we had 4 minutes. And this is going to give us a charge in coulombs. Okay, but we want to know how many electrons this is. And my software doesn't have an equation for like how many electrons there are to make a particular amount of charge. But that's all right. It's a pretty easy equation, so we can just add it in ourselves. The total charge is equal to the number of electrons times the charge on an electron. It seems legit to me. So now let's equate these. Now we want to know the number of electrons there are. So I double-clicked on the number of electrons. And again, we want to rewrite this in terms of this equation. So I'm going to drag from here to here. And now I'm going to give it the charge on an electron, which I happen to know is 1.6 e to the minus 19 coulombs. And do that. And there we go. That's a bunch of electrons. Okay, let's do one last problem. So we have 2 equally charged particles that are held 3.2 millimeters apart, released from rest. The initial acceleration is 7 meters per second. The second one has 9 meters per second. We know the mass of the first particle. We want to know the mass of the second particle and the magnitude of the charge of each particle. Let's do it. So we have an electric force here, so we're going to want Coulomb's law. And we have some accelerations, which are of course related to forces by Newton's second law. And we have 2 different particles and 2 different accelerations. So now we have 3 equations for forces, but these forces are all actually the same. The forces produced by the electric force are equal and opposite. So we can just declare them all equal. Now let's sub in all the facts we have, which are 2 accelerations, a radius, and a mass. The first particle was 7 meters per second. the second was 9 meters per second. Okay. The mass of the first is 6.3 e to the minus 7 kilograms. Okay, now we can get the radius in there as well, which is 3.2 millimeters. Doop, doop. And now let's make the, let's solve some stuff. So the second one has this mass here, which is given by force divided by the acceleration on it. We can rewrite that using this equation for force, and here's our answer. And these are pretty similar to each other, which seems pretty reasonable. Let's try and solve for the charge. So let's get this first one. So the charge is this function of the electric force equation. Let's rewrite this in terms of the force we know more about. And we get this result. And looking at this result, I actually suspect that the problem as asked cannot be answered. Because you see we have the charge of the second particle in the denominator there. And if we solve for the second particle's charge, we'd get the same thing with the charge of the first in the denominator. And I think this is what this is telling us, is that given the facts, all we can actually say is the product of the two charges. We can't actually say anything about how much charge is distributed in one versus the other. Like, if you have 1 coulomb of charge in one thing and 2 coulombs in the other, that's exactly the same as if you had 2 coulombs in the first and 1 coulomb in the second. So I'm going to claim that this problem is actually impossible as written. But that's fine. Let's solve it for some fun cases we invented ourselves. So to start with, let's just do it with, let's assume that the second charge is an electron and see what that tells us about the charge of the first. So an electron has charge 1.6 e to the minus 19 in coulombs, and so if we sub that in, we see that our first particle has a much larger charge in coulombs. That makes sense. Note that these numbers are very different. I'm kind of curious what this charge would have to be if they both had equal charge to get the observed accelerations. So let's solve for that. So I'm going to declare these two variables equal. Now I can rewrite QB using this equation, and I can now write force using this equation. And here we are, here's an answer. So if the two charges are equal, then their charges are about 7 times 10 to the minus 11 coulombs. And that is my physics software.